Okay, time to get into the math. We're going to do our rate laws over this series of the next couple lessons. These are a little bit more challenging, so you're going to need your worksheet packet. We're going to go with worksheet 5, Kinetics Rate Laws number 1. You're going to want a calculator, and you're going to want your notebooks, because I think you're going to want to take some notes on this before we actually get into the math. So, these are math-based problems, but we'll also have to apply some logic in some of the later, more complex problems. It's definitely easier for most people, myself included, if we're working in whole numbers as opposed to fractions. What do I mean by that? When you're considering the proportions that are given, put the big number in the numerator and the small number in the denominator. So you'll end up with something like 2 or 4 or 16 as opposed to 1/2 or 0.25, etc. It's just easier to work in whole numbers. So when you're studying rate laws, what's going to happen is you're measuring the effect of changing the concentration on how fast a reaction is going. So the brackets always stand for moles per liter, and that works fine for solutions, anything aqueous. That also works for gases. You can't express the concentration of a pure liquid or a pure solid, but we'll get into that more later. So just so you know, this means molarity, moles per liter. It's good for solutions and gases. So you're going to change the concentration, and you're going to see what effect it has on how fast the process is going. This is generally done using photospectrometry. All right, basically using light. You're measuring the intensity of light as a reaction proceeds. So you have a reaction vessel, you put in your reactants, they start to disappear, and your products, they start to appear. You use a wavelength of light that is tuned to one of your reactants or products, that particular wavelength interacts with that molecule, that type of molecule. If you're forming more of that molecule, you're going to be blocking more of that light. If you're using up that molecule, you're going to be blocking less of the light. So you've got your reaction vessel here, you put in your reactants, you've got your specially tuned wavelength of light to interact with your reactant or product. The light's going through the vessel and it's being detected on the other side. So if a reactant disappears, more light's going to reach the detector. And if a product is appearing, less light's going to reach the detector. And you measure the intensity of that signal over time, and that directly correlates to the rate of formation or the rate of using up, disappearing your reactant, forming your product, using up your reactant. Now, you don't need to measure every single reactant or product, because if you know one, you know them all, because that system is related through stoichiometry. So if you've got a system with 1A and 2B and 3C and 4D, that stoich comes into play. You don't need to measure A and B or C and D. Just pick one of your players in the game, and through stoich you have them all. So there are a lot of different ways that a reaction might be changed by altering the concentration of the reactants. For our purposes, and our purposes in this class only, we're going to consider 3 scenarios. That's not too bad. Okay? First one, what if you change the concentration and nothing happens? They call it zero order. Yeah, I doubled it. It didn't get any faster, it didn't get any slower. Oh, it has no effect. You're going to come to like those. That makes your life a lot easier in these problems. So if you double your concentration, the rate is not affected. The rate would just stay flatline as a function of concentration. Yeah, it doesn't change at all. That's zero order. What if you have a matching effect? So I took my concentration, I doubled it, and hey, it's going twice as fast. It does whatever I do. I took my concentration, I tripled it. Yeah, it went 3 times faster. I took my concentration, I quadrupled it. Yeah, it went 4 times faster. It's matching it, 1 for 1. Well, if you had rate as a function of concentration, you'd get a straight line with a slope of 1. We call that first order. And our last case scenario, what if we had a squared effect? I took my concentration, I doubled it. Yeah, my rate is 4 times faster. Well, 4 is 2 squared. I took my concentration, I tripled it. and it's 9 times faster. Yeah, 9 is 3 squared. I took my concentration, I made it 4 times faster, 4 times stronger, and the rate is 16 times stronger. Well, 16 is 4 squared. 2, 2, 2. These are called second order relationships. Second order squared function would be half of a parabola. If this is your rate and this is your concentration, that's not going to be a straight line, that's going to be curved. So, the general form for a rate law that you are responsible for determining based on a series of data. You say the rate is always equal to some constant K times the concentration of the reactants to some order. Your job is to figure out that order. Notice, concentration of the reactants. Changing the concentration of the products is not going to affect the rate of a reaction. The reaction has already occurred. This rate law constant K, that's a lowercase k, it's not the capital K that we're going to use later. Okay? It's specific for this system, and it depends on what conditions you have. So you can't change any other factors other than concentration. If you started to do the same reaction at a higher temperature, well, it's going to go faster just because it's a higher temperature. So you keep the pressure and you keep the temperature constant. The only factor you vary is the concentration. Your order for our possibilities here will be 0, 1, or 2. Order is nice when it's 0 because anything to the 0 power is 1 and it drops out of the equation. Okay, so generally speaking, if I had a system A plus B goes to C, my general form would be rate equals K times the concentration of A to some power times the concentration of B to some power, and your job would be to look at the data and figure out those powers. If I had something like, two H2Os go to 2 H2s and O2. You go, oh, there's a 2 there. That's stoic. That's going to come into play later. But right now, you're going to say the rate is equal to some constant K for this system times the concentration of H2O to some power. Not my products, just my reactants. Okay, we'll worry about that stoic for later problems. Number 3, what if I had 3 reactants? Well, I would have all 3 of them here, and I'd have to figure out the order for all of them. If I look at number 1 on worksheet 5, 2HI gas goes to H2 gas plus I2 gas. Okay, and we've got a series of equations, a series of experiments where you're varying the concentration of HI, and they measured the rate. They didn't tell me what they measured. Were they measuring this one? Were they measuring that one? Were they measuring that one? I don't know. I really kind of wish they told me what they were measuring, but you're asked to solve it for the general rate law equation and then solve it for that value of K in this system. So you only have one reactant. The products aren't going to affect the reaction rate. So you say rate equals K times HI to some order. Now don't forget the K. People tend to forget to write K, and they get the problem wrong because they forgot to write K, and it's not as good. Okay, so your job is to figure out the order. And this K, it's going to depend on, whatever conditions you were at. These just would have to stay the same. Don't forget to write K. All right, so here's our scenario. This is just a recreation of the data. Don't worry about the units for these rate laws. How often do you hear me say that in chemistry? Almost never, right? We're talking about moles per liter per second, and they're changing, and then we're going to multiply them together, and some of them are going to be squared and whatnot. So we're going to leave the units out, and you can take that up with Mr. Bauer when you take AP. I wish they had told me what they were measuring. They didn't tell me. All right, whatever. Here are the concentrations of the experiments that they did, and they measured the rate of appearance of one of these or disappearance of that. Okay, they didn't specify what it was, but once again, put the big numbers over the small numbers. Don't work down, work up. You want to say, well, I doubled something, not I cut something in half. It makes life a lot easier. So if I look at experiment 2, 2 times 10 to the minus 3 is bigger than 1 times 10 to the minus 3. Going from here to here, I would say I doubled my concentration. Yeah, that's 2. What happened here? Well, put the big number over the small number, that's 4. That's 2 squared. Oh, considering this series of experiments, I would say that the concentration of HI, when it doubles, the rate goes times 4. The equation, the system is second order with respect to HI. And if I had chosen a different series of experiments, that's okay. What if I had chosen experiments 1 and 3? 3 times 10 to the minus 3 over 1 times 10 to the minus 3. Oh yeah, that's tripling, right? What if I put the big number over the small number here? So, once again, this is tripling. What is this? Big number, 10 to the minus 4 is bigger than 10 to the minus 5. That's 9. Oh yeah, 3 squared. Either way, I ended up with an order of 2. So, it doesn't really matter which series of experiments you consider, but you have to consider 2 experiments, come up with the proportionate change with respect to that reactant, and then come up with the proportionate change of the rate. And it will either be 0 order, 1st order, or 2nd order. So now I could say, well, my rate law equation really boils down to rate is K times HI to the 2nd power. There's your 2nd order. So that, we'll go right here. They put in K for you, okay? So this is a key. They put in K. We have one reactant. It was HI. We figured out the order was 2. Next job is to solve it for K. You could pick any of the experiments, plug the data in, and solve it for K. They gave you the concentration. They gave you the rate. Your only unknown is K. So if I go to experiment number 1, that's my concentration, that's my rate. Plug them in. 3 times 10 to the minus 5 equals K times 1 times 10 to the minus 3 squared. I'm going to divide out to get K alone. Plug and chug. K turned out to be 30. Now, I could combine these and say, well then, my rate law is really rate equals 30 times the concentration of HI squared. All right, so that's the first problem from rate laws. I would like you to try for me number 2. There's also only one reactant here. All right, we'll worry about additional reactants tomorrow. Just try for me number 2 tonight. Thanks much.